Can we campaign?
If we get some ad revenue going.
Yeah.
Okay. So I was, over Christmas I was thinking about recording because, students do miss lectures, and sometimes they're valuable nuggets. Watching the lecture can help. So I know if you want that, I can take a look into recording and posting and running a YouTube channel and monetizing it and all that. Okay?
Ask Mr. Louie.
Yeah.
I looked into it. We need to get 2,000 watch hours first.
Yeah.
Someone get a formula. Someone get an algorithm going.
Get a bot. Let's go.
Yeah.
Okay, so today's lecture is about section 5.3, okay, and I'm actually going to deviate.
Yeah.
Up to this point, I've been like slavishly following the textbook, okay? I didn't care for the presentation in section 5.3, so I'm going to try to do it a little bit differently, and if nothing else, you're going to have two different explanations of the same concept, and maybe one of them actually appeals to you, and you go, oh yeah, I finally get it, okay? So let's first of all take a look at right triangle geometry. So you guys over here in this corner, I'm always blocking you. So tell me to stand to the side or something like that if I dwell on this side of the board too long. Okay. So we have. Let me do a sound check. Brett, how's the sound? Sounds good. Okay. Want to make sure. Just want to make sure. Okay. So back in AGS 2, something like that, we were doing right triangle geometry, and that led to right triangle trigonometry. I've been spelling trigonometry wrong all this time. There's an extra O in there, but anyway. Yeah, it's trigonometry. And initially, I thought it was because I grew up there, but no. Apparently the British spell it the same way. Trigonometry. Okay, so we have a right triangle and you've seen this all before, and you remember, tell me you remember SOHCAHTOA, right? This is all from right triangle geometry, and so this is angle theta. So the sine of theta was equal to opposite over the hypotenuse. So it was A over C, and the cosine of theta was equal to B over C, and tan of theta is equal to A over B. Close bracket there. Okay, so you remember all of this, and this defined trigonometric ratios, right? Sine was defined as a trigonometric ratio of opposite over hypotenuse and adjacent over hypotenuse. So these were so I'm not going to spell trigonometry anymore. I'm just going to go trig. I'll be a lot easier. These were trig ratios, okay? And these are proper definitions of sine, cosine, and tangent, okay? So this is all like, yeah, I remember this, okay. So if, sine or cosine are ratios in that if I were to draw a different triangle where A is much longer, but we have the same B, so A and C change and theta changes. So A and C change, so A and C change and theta changes. So these are, so if I change this triangle. A gets longer, C gets longer, theta gets bigger. So they all kind of like moved together to give you ratios, okay? And we calculated those out, or you punch them into your calculator. And so as a trigonometric ratio, sine captures these changes, okay? So, but we're gonna move beyond being bounded by right triangles today, okay? Okay. No, we're not going to go and do left triangles. We're gonna go and do unit circles. Oh man.
What about wrong triangles?
The wrong
What?
triangles. Okay. So
Where are the up triangles? And the
so
down
if
triangles.
we have
They're
a
on
unit circle here, okay?
Right.
So this is 1 and 1. Okay,
Is it down triangle in a triangle?
I'm going to present this as a unit circle. The book presents this as an arbitrary circle with radius r, and that's okay too. Okay, but I'm thinking you guys can skip that and go right to the unit circle because you guys are period 5. I know what that means. I know what that means. Okay. Okay. Draw. Here. Let me use the. So if I draw a right triangle in here, yeah, okay, we're going to do right triangle in here, and this is theta, and here's my right triangle. And so this being in the unit circle, at this point being on the unit circle, this radius is 1, and therefore the hypotenuse of the right triangle is 1. Okay, so what we can do here is we can look at this right triangle and we can say, well, this point here, x, y, we can say this point x, y as y is equal to what? In terms of right triangles, we can say, oh, it's a over c, so it's so this is y. This is the y here is equal to c. So sorry, let me write it exactly as we have it before. Okay, so we have sine of theta is equal to a over c, and so we can say c is equal to a sine theta. That's not a sine theta, that's a times the sine of theta. Okay, so we can say that sorry, that is not correct at all. Okay, so a is equal to c times sine theta. Okay, sorry, I need to mark myself down for careless errors. Okay. But you know, there's a funny thing when you're presenting, especially when you're presenting online and being recorded, is that suddenly your brain turns off.
Yeah.
We don't exist.
Okay. So I'm glad I didn't do a PhD because I had to defend it, you know, in front of a panel of professors, and that would be challenging to do. Okay, so we can use this, which came from over there. We can say y is equal to c, which is 1 times the sine of theta. So y is equal to sine theta. So, oh, well, that's kind of interesting. Well, you know, I can also do the same thing with cosine of theta. Is equal to b over c, which means b is equal to c times cosine of theta. And we're going to get x, this distance x here, right? Which is, and this x is this, yeah, here I am, dwelling on the left side of the board, okay? So this x here is the same as this x, right? That's the kind of the definition of the Cartesian plane. So x is equal to 1 times cosine of theta, which means x is equal to cosine theta. So wait a minute here. Are you saying, am I saying, are you saying, no, you guys aren't saying anything. Am I saying that this is cos theta comma sine theta? Wait. So now I have, what do I have? I have a point in space that's defined by sine and cosine. It's like, ooh, that's kind of weird. That's a little unexpected. Okay, and so this is so we can describe this point in terms of cosine theta and sine theta. So, well, what can we do with that? So if so what we can do now is we can erase this. Yeah, I know you guys hate this whiteboard advantage, and we can erase this. We can erase this if we know this is on a circle. So here's this point in space that's defined by, that's located using sine and cosine. Okay, and it's a point in space located by sine and cosine, but it's not using trigonometric ratios. It's using these trigonometric functions. Okay, so this is, we're moving beyond a right triangle and moving into treating sine and cosine as functions. Okay, so what's a function? You shove something in, you get something out. Shove something in, get something out. Okay, so whereas here, back in right triangle geometry, you were kind of limited to this, well, right triangle. Okay, and you could, and we'll see in just a sec that we are no longer limited to right triangle geometry. So let's take a look, see. Okay, so one of the fallouts of this is that tan theta, okay, which is a over b, which is x, a was c sine theta, so it was a over b, which really c sine theta, and this was c times cosine of theta. So tan theta is really just sine theta over cosine theta. But this is, I guess you could call this a corollary. This falls out of the work that we've done here. Okay. Okay. So let's define this a little bit more. Okay. So cosine theta is the x coordinate, and sine theta is the y coordinate. Okay, just to be clear. And this is so let's go over here and let's talk about x is equal to cosine theta and y equal sine theta. So what is this theta? So this theta is the angle between the positive x-axis and the angle that what was the wording that I put here? To the radius that goes through, that goes to this xy point. Okay, so this is the theta that we're talking about here. So still no right triangles. We have abandoned right triangles. How completely have we abandoned right triangles? Well, look, let's take a look at, let's say, what is this point? This point is supposed to be 1, 0, right? Well, what's the angle at this for this point here?
0.
0. So have you lately seen any triangles with angle 0?
It would be a triangle.
How about this one over here? What's this one? 0, 1, right? What's the angle there? Okay, so I can get, so this is sine of
450.
90,
Yeah, 90.
90, and this is going to be cosine of 90. So I can actually compute this. I can compute this. In fact, you can go compute it in using your calculator, right? It's 90 degrees. So you guys aren't fourth period. Fourth period still has a calculator out. I keep forgetting to nail them to the wall. Yes.
Cosine the x value and sine the y.
Yeah. And the way to so sidebar, okay? Cosine is related to the x, sine is related to the y, and the way to remember that is that C comes before S in the alphabet, and so does X come before Y. Okay? It's like, oh, fortunately, there's a little mnemonic to, or something like that. Okay? So I can actually compute sine 90, and I wouldn't be able to do that if I was still stuck in the right angle triangle domain. Okay? Well, I personally haven't seen any right triangles with 90-degree angles in them, except for the one that's supposed to be there, right? What about over here? What about over here? What about this point?
180. -1, 0.
-1, 0. So, and it's 180 degrees. So this is a pi, or 180 degrees. Boy, I really haven't seen any of those triangles lately. So now, and here I can get cosine 180 -1. Wow. This is way beyond the right triangle universe. Okay, so this is like those 2D games that you play. I don't know, maybe to the plane of your screen, you gobble things up.
It's a platformer to an open
Yeah.
world.
But then, if you could actually leap over, now you're in a totally different space. Okay, that's my analogy for you today. Okay, so we have now
Oh gosh,
broken
don't
free
even talk about Terraria.
of right triangle space, and we're going to let sine and cosine and tangent, as a result, be free. Okay, they're now to be considered functions in all of its functional glory. Okay, and that means you shove something in, you get something out. Shove something in, get something out. Okay. So this is important to be able to treat sine and cosine like functions in. I forgot to do an exercise with you guys at the beginning. Very well. That's okay. We will catch up
I mean, this was just a good
at the end.
review.
Okay,
so-
we were supposed to do a fun group exercise, but then I started taking attendance and I totally forgot. Fairly typical. Okay. So this leads to. Okay. So the equation of this circle is x squared plus y squared equals 1. Right? No one disagrees with that, right? Well, what's x squared? Or what's x?
Square root of x.
So it's cosine theta squared plus, well, what's y? Sine theta squared. So this leads to this Pythagorean identity. And we can, we'll have the short form of this. Easier way to write this is just cos squared theta plus sine squared theta. Okay? Equals 1. So this means, this cos squared theta means cosine theta times cosine theta. Okay? It doesn't mean anything else. It doesn't mean cosine of theta squared. Okay? So it's very explicit about these brackets, and this is an interpretation. So the analogy here is from last semester. Remember we did f of x, and so, you know, we'll say x plus 2. If we did f of x squared, so that'd be x plus 2 all squared. We can also write this as f of x, f squared of x. Okay? You may not have actually encountered this nomenclature in semester 1, but you are now. Okay? And we're applying it to sine and cosine because it's a whole lot easier to write. Okay? So the other way to introduce this is if you had g of x equal x squared and plug those things in, but you guys don't want to do that anymore because you had the exam on that and you want to forget about it. Okay, so next thing we're going to do is go back to this unit circle here. I'm going to outline for you what we're going to do in as an exercise. Okay? So I'm going to do all the easy ones. Okay, so you have your unit circle, and this is you have your unit circle. I like the idea of drawing these other ones as dotted lines, but this is you can do 45 degrees. And in radians, this is going to be, what is it?
5 over 4.
5 over 4?
Pi over 4.
Pi over 4. The stupid math got in the way. Pi over 4, and what are the xy coordinates of this guy? Okay, so we can figure that out using geometry here, right? We can go back to right triangle geometry, and we can go, oh, this is a 45, 45. Remember we did this on Monday, 45, 45 triangle, and oh, if this is 1, this is a 1 over root 2. Do you remember that from Monday, or did it already get wiped out? Is your memory buffer so small that, you know?
Yeah.
They
Yeah.
just had them memorized.
Last,
One day.
last in, first out. Okay. Okay. So this is, and we can write this as root 2 over 2, right? You remember normalizing these square root denominators? Okay.
Why do I want to try that?
And so we can write cosine of pi over 4, which is equal to cosine of 45 is equal to root 2 over 2. And we can write sine of pi over 4. Strictly speaking, we should put in these brackets, okay? And I would urge you, if this argument gets kind of complicated, to put in these brackets so that you don't commit algebraic errors like dropping a minus sign or something like that. Cosine of 45, which is equal to root 2 over 2. Sorry if I wrote that a little small. Okay, now, the next, so what we're going to do is we have root we're going to gather together in groups. Okay, how about, let's see, there's one, okay, how about you 5 together? Okay. Sorry, as I've mentioned before, I hate handing out paper because I'm always afraid I'm going to get a paper cut.
Just get thimbles for every single finger.
Yeah, or rubber gloves or something like that.
Yeah.
Okay, and then you 6 get together.
Yeah.